Let's look at balancing chemical reactions. Now, notice on the slide I have written down chemical equations, but I'm calling it a chemical reaction. It's because it's the same idea. A chemical reaction is what's actually happening. It's these things are going in, they're reacting, they're producing these products. Okay, and we're going to talk about all those in a minute. But we treat them as equations because of this idea of law of conservation of mass, which is a fundamental law, and we know it's true that basically if something goes into a reaction, it has to come out on the other side. It doesn't mean that the same compound has to go in, but however many atoms of whatever elements I have go into the reaction, they have to come out on the other side as well. So, writing and balancing chemical equations. In order to correctly calculate quantities in the chemical reactions, we need to use a balanced equation. We need a balance because that shows us exactly how many things are actually reacting. A chemical equation is a symbolic representation of this chemical reaction. It's in the form of symbols and formulas. So, our chemical formulas, some of the symbols will include not only chemical formulas, but the physical states that these species are in. We'll talk about that in just a minute. We'll identify reactants versus products. If we have heat or light or catalyst included, that will often show up in a balanced chemical reaction as well. The reactants are always on the left-hand side, the products are always on the right, the arrow is always in the middle. So you can see up here, reactant side versus product side with the arrow separating them out. Okay, and so you see here we've got chemical formulas. Below here, we've got your space filling models. They're both representing the same thing. The space filling model is just showing you what the molecules actually look like, whereas the top one is just showing you chemical formulas. But it's always reactants on the left-hand side, products on the right. Throughout the course, we will also talk about reactions that could be what we call reversible. They could go either direction. We still treat them as reactant on the left and product on the right. It is always written that way. That's just the convention. So, reactants are substances that are initially present in the chemical reaction. They're consumed during the reaction to make your products. And again, your reactants are on the left hand side of the arrow. Products are the substances that are formed or produced in the reaction, and they're found to the right side of that arrow. Notice too that the arrow is like this, okay? So that means a forward reaction as written, but it is a full arrow. When you're balancing equations, we do follow a set of rules to balance equations. You don't have to follow these rules, but I find it to be the easiest way to get a balanced reaction. So first, identify your most complex substance. Starting with that substance, choose an element that appears in only one reactant and one product when possible. That's not always possible. Adjust the coefficients to obtain the same number of atoms of this element on each side. And we'll talk about what coefficients, superscripts, subscripts, all of that mean. Balance polyatomics if present as a unit when possible. That's not always possible, but it is possible a lot of the time. Balance the remaining atoms using fractions as necessary. You will often need to use a fraction if you have a diatomic. Not always, but often. Okay, if you have a diatomic present in your reaction. If a fractional coefficient has been used, multiply both sides of the equation by the denominator to obtain whole numbers for all coefficients. Check your work by counting the number of atoms of each kind on both sides of the equation and be sure to include the chemical equation. Be sure to check that the chemical equation is balanced at the end. So let's talk about the different pieces of a formula. So I know we've discussed this already in previous chapters, but just kind of really solidifying this for you guys. Remember that the coefficient is the number that's out front, and that is applied to all elements in the formula. So here is my coefficient. If I had written 3 KMnO4, so this means 3 potassium permanganate, that 3 applies to everything following it. So that means I have 3 potassium, I have 3 manganese, and I have 3 times 4, or 12 oxygen. Subscripts, so you can see subscripts here and here. Okay, a subscript is applied to the element it follows, not the whole molecule. Now, here on the aluminum, it's following the aluminum. That means I just have 2 of that. When the subscript follows the polyatomic, it does apply to the whole polyatomic. So here in KMnO4, I don't have any subscript on the potassium, so I have 1 potassium. I don't have a subscript on the manganese, so I have 1 manganese. But notice here I have 4 oxygen, so that 4 means I have 4 oxygen atoms in this molecule. If a subscript follows parentheses, it counts for the entire polyatomic. So again, this means I have 2 aluminum. This 3 means I have 3 sulfur, and 3 times 4, overall 12 oxygen in this formula. Other things you're going to see are physical states, and you do need to get comfortable with using these. First up are gas. If you see, and these are, notice they're all lowercase letters, okay? So a lowercase g means that that compound is in the gas phase. A lowercase l means that compound is in the liquid phase. A lowercase s means it's solid. And a lowercase aq. AQ stands for aqueous. What it means is it is dissolved in water. We'll spend a lot of time with aqueous systems throughout this class and the next one, and you will get more used to that, but you will see some aqueous in this chapter as well. Energy symbols can be used above the arrow, so sometimes you'll see a reaction where say you've got A plus B going to C, but you see a little triangle above. That means that the reaction has been heated. We don't always put that in, but sometimes it is emphasized that way. You may also see a little H nu. That stands for light. So UV light has been used to get the reaction to go. And then catalyst can also be listed above the arrow. So sometimes you'll see something like the manganese for oxide here, where you see it above the arrow. That means it is a catalyst in this reaction. Let's work a few examples. Balancing equations. So again, remember you need equal number of elements on each side of the equation, and be cautious of your states of molecules. They should still balance out, but you may be changing a physical state. So I may be going like H2O liquid to an H2O gas. I have to pay attention to what my phases are as well. So first up, this one should be balanced. Let's just check it. What I like to do is I like to write down all the elements I have. I have iron, carbon, and oxygen. Iron, carbon, oxygen. I like to write them on the same spot under the reactants and products. And then if balanced, they should match. Here I have 4 iron, 4 carbon, 4 times 3, so I have 12 oxygen. I have 2 more oxygen right here, give me a total of 14 oxygen. On the so again, that was iron 2 carbonate reacting with oxygen on my reactant side. On the product side, I have iron 3 oxide and carbon dioxide. The 2 in front here, 2 times the Fe here, but I have 2 Fe, overall 4 iron. 2 times the 3 here on the oxygen. That gives me 6 oxygen from the iron 3 oxide. 4 carbon, and then 4 times that 2, so 6 plus 8, giving me overall 14 oxygen. So checking it, this reaction is balanced and we are good to go. What about the other one? Let's see. I've got iron, oxygen, and hydrogen. So I always write the elements on the same spot in the same order on the other side of the reaction. First up, I've got 3 iron here, 4 oxygen here, and 2 hydrogen here. When I look at my product side, I only have 1 iron, 2 hydrogen, and 1 oxygen. So it's clearly not balanced. So let's go ahead and balance it. I'm going to balance the iron first, so let's try it. So if I put a 3 in front of the iron here, I'm going to put them up here pretending that's fitting right there because I can't really fit the 3 in there. I didn't give myself space. That changes my iron here to 3. My oxygens still are not balanced. So let's go ahead and put a 4 in front of my oxygen here. Gives me 4 oxygens here. But that also changed my hydrogen. Now I have 8 hydrogens here. And I only have 2 on the other side. Let's go ahead and put a 4 in front of there. Now I have 8. Let's rewrite this to make sure. Fe3O4, 4H2. Oh, don't forget your states. 4H2 gas, 3 Fe solid, and 4 H2O liquid. And just to check to make sure I did it right, I'm going to erase this and check it. So on my reactant side, I have 3 iron, I have 4 oxygen, and I have 8 hydrogen now. I don't think I can, the 3 kind of fits there, I guess. On the product side, 3 iron, 8 hydrogen, and 4 oxygen. Now it is balanced. So 2 more examples. When butanol C4H10 or C4H9OH is burned in oxygen, CO2 and water are the products. What is the coefficient in front of the O2 in the balanced equation using only whole numbers in the lowest whole number ratio? So C4 H9OH. Now, you can leave it like that, or you can simplify this, and you can write this C4H10O. I recommend rewriting it and putting hydrogens together so you don't miss one, okay? The reason it's written like this is showing how the compound is showing it's an alcohol. In alcohols, it's an organic functional group. The OH at the end of the compound makes it an alcohol. And so writing it that way is basically hyper emphasizing that it is in fact an alcohol. But when I'm balancing, I want to keep it as simple as possible. Put them together. This is burned in oxygen. So remember, oxygen is O2. It's one of your diatomics. It's a gas. Butanol, it doesn't say it here, but butanol is, I believe, a liquid. If you have to put phases in, if I graded you on phases, that would give you enough information to figure out the phases. This forms CO2 and water. So let's go ahead and look what we got. We got carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. Clearly, me where I'm writing these isn't working. I love that scribble function when it actually works for me. Okay. Now, looking here, I've got 4 carbon, 10 hydrogen. I've got 2 oxygen here, and don't forget this guy here. I got 1 oxygen here. On this side of the reaction, I have 1 carbon, I have 2 oxygen here, and 1 here. And I have 2 hydrogen. When you are doing combustion analysis, trust me, the easiest thing to do is balance everything except your oxygens first. Everything else. Start with your carbon, then your hydrogen, then your oxygen. So my carbon, I need 4. I need to make a 4 here. How do I make a 4? I put a 4 there. Of course, that changed my oxygen. Now I have 8 plus 1 oxygen. Next, I need to balance my hydrogen. I have 10 over here. I need 10 here. So I'm going to multiply this by 5. When I did that, that changed my oxygen. Now I have 8 plus 5, overall 13 oxygen. It takes a minute to get used to. But notice I have 13 oxygen on one side, 3 on the other. Playing the game back and forth to get them to balance is going to be a nightmare. But I recommend you need 1 right here. Okay? That gives you have 1 right there, plus x has to equal 13. So I know the x has to equal 12. 1 plus x equals 13. Therefore, x has to equal 12. Okay? If I put a 6 right here, that's going to give me 12 right there. Don't forget the oxygen right here. People are going to forget that one. Now let's check it. Let's rewrite this and check it. C4H10O, 6O2. I'm going to keep the phases out right now just for space. 4CO2 and 5H2O. Carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. I have 4 carbon, 10 hydrogen, 1 plus 12, 13 oxygen. 4 carbon, 2 oxygen. I'll come back to the rest. Oh, wait, you know what? Nope, that's 8 oxygen. 4 times 2 is definitely an 8. 5 times 2 is 10 hydrogen. And then 5 times 1 is another 5. 8 plus 5 is 13. I have balanced it. But then it's not the question. The question is, what is the coefficient in front of O2 in balanced equation? 6. So the answer to this question is just 6. Okay, what numbers belong in the blank spaces to fully balance the following reaction? I've got iron reacting with chlorine gas to form iron 3 chloride. I've got 1 iron and 1 iron. That's helpful. My chlorines aren't going to be helpful here, though. They're going to throw off that iron. Notice the 2 here and the 3 here. I got to find my lowest common multiplet. Only way to balance that is put a 2 there and a 3 there. That gives me 6 chlorines on either side. But notice that threw off my irons. Now I'm going to have to put a 2 here for the iron. So it's going to be 2, 3, 2 for my answer.